Hey everybody, thank you for tuning in to our next devlog as we build our own custom RPG engine in Unity using some software architecture best practices. Okay, so what are we solving today? Well, today we've created and implemented a rules engine, RULES, to decouple our systems logic and game logic and system rules for the mechanics away from the code implementation. So just like always, we'll start with a quick demo here. So what do we have? Okay, well, we see some new controls on the screen here. We see a PC level with a slider, a combat rule button, and a decision. So what is this demoing? Well, we have this component wired up to a rules engine, and what's going to happen is suppose you have a player character and they are going to encounter a boss or mid-level boss or whatever, some kind of strong foe. And you think to yourself, well, there's a lot of different ways to balance a game as far as the mechanics go. And one strategy is to scale the enemies based on your current level. So that way, it doesn't matter at what point in time in the game you encounter a particular enemy, it will always be um, relatively challenging according to your current level. I personally am not a big fan of that design choice. Like, take for example a Metroidvania game where there's probably a lot of backtracking and stuff like that. And if I have to backtrack through an area and I've spent all this time getting upgrades, new abilities, new techniques, and it doesn't allow me to just wipe a room quickly. What was the point? What was the incentive for getting powered up? And some people like that system, and that's fine if you do. Whatever, it's fine. I think for what I'm trying to build, a better approach is to, let's say you're level one and you say, hey, I encountered a boss. I'll just get the normal boss. I'll allow the normal boss fight. Maybe I climb up a few levels. Oh, still allow it. But what happens if I'm at level 25? Oh, well, now we can spawn an elite enemy. Interesting. So, how did we do that? Let's take a look at the scene editor. And we've got some new stuff over here in the scene. We have a combat rules demo script. No surprises here. It takes a Text Mesh Pro text field and a slider component. We've got our PC level text here and the decision from our rules engine. Let's take a look at this combat rules demo script. Oops. Switch over to our IDE and take a quick look. All right. Oh, we can get rid of this reference. It's not used. Very good. Okay. So no surprises here. We've got our serialized field backed properties. And now we have a rules string. And what we can see is this is very human friendly, right? Um, whether you're a developer or like in terms of like writing code, or maybe you're a game developer who's developing narrative or game system mechanics. Uh, you want to be able to test new rules without having to refactor a bunch of systems that may or may not be tightly coupled. Hopefully, they're not tightly coupled since we're using an event bus. A very simple implementation of an event bus, but no need to over engineer it until we need to over engineer it, right? So now we've got this rule string. So we open up, we define a rule called high level boss. We'll give it a priority, and priority is useful for ranking which rule should take precedence. So this rule says that when player.level is greater than or equal to 20, and the enemy tag is boss, then the outcome is going to be spawn elite with, let's say, tier 3, could be tier 3 loot, tier 3 abilities, tier 3 whatever. This is just arbitrary. Maybe we want to drop some legendary loot, and then we stop the rule. And we have a fallback rule so that our logic doesn't fall apart. And the outcome is just going to be allow. We could word that better. And say we'll get a fallback. So just fall back to the normal encounter. All right, so on the demo, we can see the basic interface of how this works. We're going to need a rules engine, and we'll create a dictionary with string keys like player.level or enemy.tag, right? And it's going to have a rule value. Why don't we close all these other tabs? Let's go to the definition of this real quick, or the implementation. Oh, I'm sorry. Go to the definition. All right, so we can see that the rule value is a read-only struct. It's kind of big, uh, but you can see that it takes a rule value kind, which is an enumerated type, and it's got some methods. Looks like we have some, I added some cast, but maybe we don't need to have some cast. Oh no, I'm sorry, this is the constructor. Duh, I've been up too long. Anyway, so we got some logic to throw things if, if we can't convert them properly. And okay, we can try to get some numbers. We can check if something is truthy, whether we call that truthiness, false, uh, you know, null is false, bool that's not equal to zero, integer that's not equal to zero. We could do some absolute values on a float 64. Maybe that's zero, right? And and if a string is null or empty, that could be falsy, and we could just default to false. So we'll assume things are true unless we need to make them false. And again, we can go through all this kind, but we're just basically switching over types based on the situation. And we have some operator overloads or some new operator definitions. And again, all of this is on GitHub. Post a link in the video description. So anyway, we come back, we got our dictionary of facts. And when this game object is enabled or goes to the onEnable event, we want to instantiate our rules engine builder. Excuse me, yeah, we're going to instantiate our rules engine by calling a builder, and we're going to give it the rules from our text and our rules private string here, and we're going to explicitly enable trace. You can see it's true by default, and then we're going to build the rules engine. So we have here a nice Fluent style interface to this builder using the builder pattern. And this decision method is what's wired up to the button in the Unity scene. And we can say we're going to add some facts, right? So we're going to say that the player.level is from the level.value slider. And since the slider values are floats by default, even though we locked it in to whole increments, we want to cast, we want to, you know, we want to round our, we'll use Unity's built-in math utilities to round our floats to the closest integer. And then from that, we'll create the int and we'll put it in our rules dictionary. And of course, we have our enemy tag from a boss. And now here's where the magic happens. So our decision is going to be the result of our engine evaluating a dictionary rule context full of facts. All right, let's go to the implementation of this. So you can see this is fairly simple. It's a sealed class. It implements rule context. It's got a dictionary of facts, same signature as what we're passing in. Um, Yep, we got this right here. This is our constructor. And we can see we're using modern notation, so we're just going to use the rocket operator here. And we're going to try to get a value. And we'll pass in an out rule value by reference from calling that method. So pretty simple, not a lot going on there. It's a nice, clean, simple interface. And of course, we want to wrap some critical things in a try-catch block, especially while debugging. We want to be able to catch exceptions. It's not a great practice to catch every exception as exception type, and that's the base exception type. But if you don't know exactly which exceptions are being thrown, or you haven't defined any specific exceptions, you can't go wrong catching the exception. And, you know, if you are in the Go world or other languages that don't use exceptions for control flow and they have errors by value, well, there's some merits to that, you know. For example, I know when I'm writing Go, I must always deal with the error condition and I must always check it. And yes, the code can get verbose, but I have a high degree of confidence that my implementation is probably going to work in the way that I thought it was going to work. Uh, so I don't have a strong opinion one way or the other. I like using exceptions. Um, I don't like to rethrow exceptions that I catch. I like to try to handle it gracefully within whatever context is calling code that threw an exception, but that starts getting into a whole philosophical debate. But anyway, that's not important. What's important is that um, you can see we're going to make a string variable called outcome, where we get our decision.outcome. And I like to have this. You could just call it directly in both these spots, but I like to assign it to a variable. And then I can do interesting things like put a breakpoint here or put a breakpoint here and here and inspect the value of it. Okay, so let's go back and take a look at a sequence diagram real quick. Get a high level view of some interesting stuff here. All right, so we're looking at a sequence diagram, and it's just basically just kind of what we showed. So we've got some Unity gameplay code, and we need to have, uh, we're gonna, we're gonna build some rules using our DSL from text, and maybe we'll pass in some funcs, and we may or may not decide to enable true tracing, and then we build it. So that goes to the rules engine builder, right? And makes a new rule parser and calls parse rule set. The rule parser builds a new tokenizer and a new prat parser. First, the tokenizer, you know, tokenizes all of the input. And then we also have a prat parser. And what this does is this loops through the next tokens as needed. It parses our expressions, and we add a rule from our abstract syntax tree, and we sort by priority descending. So after we have our rule parser, we have our compiled rule set. We make a new rules engine runtime, and then we return back a iRules engine, something that implements iRules engine, and then we have that reference in our code, just like we showed in the demo. Let's go back to the code for a second. Let's take a look. I mean, there's a lot of code in here. I probably should have been spending some more time filling out applications for a new role, but I had to get this out of my system. All right, so let's look at the rules engine. So we've got a lot of core types in here. Okay, so maybe a good way to do this is to say, okay, well, how does build work? Well, let's go to the implementation. So build, just like we saw in the diagram, it makes a new rule parser. Uh, it parses the rule set, and then it returns a rules engine runtime. Rules engine runtime. So we get a rule set, we get our functions or no functions if needed, and enable our tracing. And when we evaluate, we need a new evaluation context, right? This context is going to have, um, well, the context of our entire rules decision. And if we need traces, we'll make a list of rule traces, or we'll just make this null. Okay. We could do a for each loop here. I don't know. I like for loops, especially if I think I'm going to want access to the index during my loop. But the first thing is we're going to call reset. We're going to get the rules, and this is why I like iterating, so we can get that um, as in at the right index. We're going to evaluate our condition, see if it's truthy. We looked at that a little bit earlier. If tracing is enabled, we'll add a new trace. Maybe asserting that traces is not null is a bit bold here, but we've already determined whether or not it should be null up here. And we should only have traces, a traces reference if tracing is enabled. So if the condition is not truthy, we're going to continue. Um, and we've got our first match semantics after the priority sorting. And so we're going to return a new decision based on our rules, you know, walking the rule abstract syntax tree, evaluating all of them, and then coming to a decision. So we got some core interfaces here. We've got our iRule context. We have an iFunction library. We're not doing anything sophisticated with that yet, but the idea is that you might be able to pass in, uh, you know, basically try to invoke the name of a function. And since we're passing a string, excuse me, the idea is to, similar to how Unity can call events by name. Let's go to hmm. So we have an implementation here if there's no functions. So then if there's no functions, then we're just going to return false. There's a lot of code in here. Well, let's take a look at the parsing. I'm particularly happy with this. So we've got a simple struct to hold our tokens. We have the different kinds of tokens that we can have in our expressions, and we can see that these are bytes. And so all of these enumerations have byte values, making them very compact, easy to move around in memory. We have our tokenizer. So if you've ever taken a compiler course, or you remember this stuff from your computer science days, or maybe you just really like hacking around in languages, tokenizer shouldn't be that much of a surprise. What this is going to do is it's going to go and take every word, every token in our rules string here, and it's going to break it up into an individual token, right? So priority would be a token, 100 would be a token, stop is a token. All of these tokens go into building our abstract syntax tree. So we're going to tokenize our string, and we're going to have a next method to get our next token. We have this interesting, let's take a look at this. So we want to basically skip white space. We want to skip line comments. We want to skip block comments. Yeah, stuff that's basically, not important for us to interpret. Okay, in the sense that it's not, logic. If we get to the end, we'll return an end of file token. And we've got a start and a character. And so now we have to go through and look for our tokens here. Now you notice we saw some curly braces in the rules, right? So we need to be able to interpret those correctly. We need to know about our two character operators. And, the way this works is that if we come across a single equal sign, we want to peek ahead. And, if you know some of your data structures, a peek in something like a queue or a stack or a heap, you can peek the next value without mutating the state of the data. Very useful for when looking ahead on your tokenizer or any other type of data structure where maybe you want to peek at the next value without mutating it or popping it off the stack or dequeuing it or whatever. So you can imagine we got a similar situation with our bang or exclamation point. So if we see that there's a not equal sign, we're going to return bang equal, right? Otherwise, we're not ever expecting to see in our current DSL any solo exclamation points. So we'll tell folks that we need to use, um, you know, the bang and the equal together. Same thing with our equal sign. If we have an equal sign by itself, we've got an issue. We've got a parse exception. So I could go back into my other code and I could explicitly catch parse exceptions if I wanted to, but I don't feel the need to do that right now. All right. Now here's an example, less than and greater than signs. Um, these, if you peek ahead and, are less than or equal, or greater than and equal, those are valid tokens, but also, less than and greater than by themselves are also valid tokens. So if the character is a digit, we'll read the number. If it's an identifier or a keyword, we're going to read those. And that's the bulk of our tokenizer logic right there, right? So we have this string, a read string method. We're gonna have ourselves a string builder, and we're going to iterate through our our source string up to the length. And this is we're going to go through and look at each character. And then we're going to append it to our string builder. You're like, oh, where's that? Got it right here. Very good. At some point in time, we're going to want to return our new token, right? Okay. So we also have read number, right? Very similar. Very similar. We're going to read identifier or keyword. Here's some a little bit of array work. working on some arrays to peek two ahead. And, you know, we've got these static methods, these helper methods here. So that's basically our tokenizer. What about our rule parser? Well, this one is fairly clean. So, we're going to we have a method called parse rule set, returns a compiled rule set. We can go see what that looks like real quick. And again, it's another small sealed class with an I only or an I read only list of rules. And all it does is it just holds those rules. So, and yeah, maybe we could have made this a struct, but the sealed class will work just fine here. Go back to our rule parser. All right, so we're going to make our rules, and I do 16 rules, a list of 16 rule initial capacity of 16. Give ourselves enough memory. Of course, since it's a list, if we ever needed to add more than 16, we could do so. Under the hood, though, this would, of course, allocate more memory and do a copy operation. It's all opaque to the engineer at the source code level, but behind the scenes, would have to allocate more memory. So if we have an initial capacity, then we can allocate maybe a little more memory than we need, but this will speed up operations overall, right? So we want to sort our rules. We want to order them by descending. So this means that the highest priority is on top. And if we were to conceptualize the rules, like if you ever played Magic the Gathering, you know that there's like a stack, right? You put things on the stack. And just like any kind of stack operation, um, last in is the first one out. So as you're piling things on top of the stack, like let's say you have a stack of magazines. I know I'm showing my age here as an elder millennial talking about magazines, but let's say you have a stack of magazines or a stack of books. Well, the easiest operation you can do, there are two. You could put another book on the stack, or you could take the top book, you could pop the top book off of the stack. And if you want to get any books that are lower in the stack, you got to pop off all the books on top of it, and then you put them back again. So there's actually a fun LeetCode challenge where you can build a queue by using two stacks. That's a fun challenge. The implementation is actually pretty simple. You just use two stacks. You use one stack for most of your operations, but then there's like maybe one key instance where you're mutating state. If you're implementing a queue with two stacks, where you have to pop a bunch of stuff off the stack, insert your data, and then move the stack back over. Maybe we can talk about that sometime, but that's probably, it might be interesting to look at data structures and algorithms for Unity, like we're already doing. What I'm trying to do is I'm trying to apply data structures and algorithms to one of my favorite topics, which is game development. So that's the whole spirit behind why I'm doing these devlogs. All right, we got a parse rule method, and we want to consume keyword rules, and we need some name tokens, and we're going to set our initial priority to 0, and then we can mutate this as our priority changes. But that's just a reference to see what our current priority is. And then, we'll go through and we'll consume our tokens in the correct syntactic and semantical order. All right. We also have an ability to parse a payload object, right? So we're going to have a ordinal string comparer. We're going to consume our left brace and our token. And so as long as the next token is not a right brace, we'll continue looping through this while true, which means this will be an infinite loop until we, uh, make it falsy. And so, yeah, we're going to just go through and we're going to parse all of these rules. And we're going to parse literal values. Now, maybe the switch, uh, we don't necessarily have to process every kind from the enum, but maybe we need to, in the future to add more capabilities. Yeah, this else is probably a little bit redundant, and you can tell that based on the two returns, but I like to have my code be very explicit sometimes, especially when you think about, hey, is someone else going to have to work on this in the future? Is that future someone going to be me? Is it going to be a peer? Who's it going to be? So I would rather have the intent be explicit instead of obfuscated behind something clever. All right, so with a lot of parsers, this is a pretty common pattern. We're going to switch over our case for our token kind, and then we have to return some type of rule value from whatever token kind it is. So for example, if our token kind is a truthy keyword, then we want to consume it so that it's no longer available, right, for the next iteration of the loop. We want to return this from a bool. So what does consume look like? Interesting question. So this is part of our Pratt parser, which we'll take a look at next. Okay, so when we call the constructor on our Pratt parser, we need to pass in a tokenizer, and we're going to immediately get the next token. Okay, we can call parse expression, and here we see consume again. Let's go to implementation here. So you can see that we're not assigning it to anything, but we do have some logic around expectations. But we want to take we're essentially saying what this is communicating is I want to consume this token. I want to take it. I expect it to be of a certain kind, and that should be correct. And then we're just going to, we're going to throw that token away, so to speak. It's been consumed. It's been eaten. Now it needs to be digested. So this is the basic format of our Pratt parser. And again, I could spend a lot of time going through this code. It's all going to be on GitHub. And that's pretty much it. I mean, there's a lot of code here, but if we go back to the rules demo, this gives us a complete demo example, and we can go through and trace out all of the code. We can reference the included diagrams, and that's pretty much it. So again, what problem does this solve? We want to be able to express rules in our game like this, decoupled from code. So, for example, let's say a systems designer comes in and says, "Hey, Ray, we need to change the encounter type for this area. Like instead of tier 3, if they're level 20, make it tier 2, or say if they're level 50, make it tier 10 or whatever. We can put any arbitrary rule that we want in there. Another improvement we can do is in order to really decouple this further, this is just a demo game object, but a best practice for production is not to have these little bits of rules sprinkled throughout different game objects or other pieces of code. What we really want is like some kind of a rules collection or rules dictionary. And we should provide a folder in our project that is just called rules outside of the code, where we can ingest these from disk, load them into memory at game time, game launch, load them all up into memory, and maybe we create singletons for different rules engines. For example, maybe we have a combat rules engine, or we have a rules engine embedded in all of the different systems that need rules interactions, and maybe those can read text files from some well-known place in the project structure, for example. So that way, somebody could come in and look at all of the rules in a central place, and then they can work on them, and without having to change any code in the game. They could cut a branch in source control, tweak with the rules, try them out, commit them, push them up, get them merged in, all that happy fun stuff. So we're on the road between our event bus and our rules engine. We're setting ourselves up for success to decouple our systems and mechanics logic away from our code implementation. Now, we don't want to over abstract it so that the code becomes a labyrinth that's hard to parse. And, we could have done just JSON files or YAML files or CSV files to express our rules. But I really, really like the idea a lot of having a bespoke DSL that's much closer to natural language, that I could spend an afternoon pair programming or pair developing with another person on a team. They understand the DSL, and then they go off and make some magic happen. So that's it. This video is getting a bit long, so we'll end it here. So, like and subscribe if you like what I'm doing. Let's connect on LinkedIn. Check out the code on GitHub, link below. Like it, hate it, love it. Remember, this is early, so if you have any constructive feedback, I'm open to it, very open to it. Um, if you have some destructive feedback, I'd like to hear that as well too. So I take all feedback. So let me know what you think. Okay, everybody, thank you so much for your time, and I look forward to seeing you again in the next devlog. See ya.